Hi guys, BuildZoid here, and we're back with the 3060 Ti that I bought. So again, thank you to the patrons for making purchases like this one possible. And what we're going to be doing today is we're going to be doing some measurements. We're going to measure the resistances of the various main power rails on the card, so that if in the future I screw something up, I know what it is that I screwed up, basically for repair purposes. And we're also going to be figuring out where all of the shunt resistors go, because there's a few of them that are very confusing. So obviously these two right here, this is for the 8-pin, this is for the 6-pin, that's nice and simple. We've got another shunt resistor on the back here by the PCIe slot, so no mystery what that's for, that's just for the PCIe slot. But then we've got this thing over here, which is like, what is that? Why is that? Like, what's that shunt resistor for? So yeah, we're going to be figuring out that as well, and I don't think there's any other shunt resistors on there. The chip monitoring all of these shunts is an NCP45491, so we should only have 4 shunt resistors on this card, as I've not noticed another NCP45491. So let's get into it. Starting off with the Vcore resistance. So we can grab a ground basically anywhere for this, but yeah, we're going to check the core resistance of the card, and it is very low, which shouldn't be very surprising. This is a fully functional 3060 Ti, and, you know, around 150 ohms, I mean milliohms, is actually totally reasonable for a modern, you know, relatively large chip GPU. Like, this is a big chunk of silicon. It's on Samsung something nanometer. I don't pay enough attention, don't really care. I think it's 8 nanometer. And so, yeah, it's really not surprising that a, you know, small manufacturing node, large chunk of silicon like this would have a very low core resistance when turned off. Older GPUs, like say an HD 7970, will have a core resistance of around 3 ohms to 4 ohms a lot of the time. This thing right here, about 0.15, 0.12, somewhere in that range. So yeah, if you have one of these, that's sort of what kind of measurement you should be expecting. This up here is the Pex Voltage Rail, and the Pex Voltage Rail has a resistance of, come on, 7 ohms. So yeah, also very low resistance, and also perfectly fine for this card. It works. This is like, it was 7 ohms before I even turned the card on, so that's in spec for that rail. Down here we have our 1.8 volt voltage regulator. Getting ground for that is a bit awkward. I'm just going to grab ground from this capacitor over here, and we're going to stab the inductor, and we get kiloohms range, which is what you'd expect. The 1.8 volt rail power is a supporting rail for the memory chips and also for the BIOS, and all of those are generally relatively high resistance devices, even, you know, when turned off. So yeah, that's a totally normal resistance over there. We have a 5 volt rail over here. Not really much point measuring the resistance on that, but we may as well. So yeah, that's in the kiloohms range, around 6 kiloohms. If you have something in like the 10 ohm range, then that probably means that regulator failed. We have another 5 volt regulator over here. Actually, I don't know why I bothered to move the card, but this is another 5 volt regulator. So we're just going to do the same thing. We're going to grab, actually this one has capacitors right on the output of it, so that's nice and simple. We can just go across this cap and to the inductor. And this one's far more kiloohms, because this 5 volt regulator, as I'm guessing, only has to handle this chip over here and then the drive for the MOSFETs. So maybe not even that. It might literally be just for powering the UP1666. It's honestly really surprising to me that MSI opted to have 2 5 volt voltage regulators on this card, because this is a relatively cheap 3060 Ti, and you know, I've seen even expensive cards opt to have just one 5 volt rail, often generated by a linear regulator, and MSI has 2 of them, and they're buck converters, which is like, okay, that's really overkill, but sure, whatever. It's not a bad thing. It's just really surprising to me that they would opt for such a massive amount of 5 volt power, relatively speaking. Anyway, for the memory resistance, we're looking at about 20 ohms, or, well, 19.4, but I'll call that 20 ohms. And that should be it. Yeah, there's Nothing, like, there's not really much point measuring something like the 12-volt rail against ground because, well, it's freaking 12-volt rail, so the resistance is going to be, you know, very, very high. Same goes for the, I'm not sure which pin it is. But, yeah, so you get the idea. So we're not going to take those measurements. So now the shunt resistors, I mean, this one is simple, right? Like, this one's just going to go to this power connector right here. And we've also got these fuses. Those fuses, when the fuses are fine, they're obviously just going to be a straight short circuit, right? So, yeah, anyway, so we've got this shunt, those are for those two power connectors. And we've got this shunt on the back, which is for the PCIe slot over here, and this one. I really want to know where this one goes. I suspect it's in line with some other shunt resistor somewhere, so... yeah, let me just check something. Okay, I was right. That's... you can actually see the 12-volt power plane for that power connector. Whoa, I got it. So this one, there's two shunt resistors connected to the 8-pin power connector. I don't know why you would want to do that. But, you know, it's an NVIDIA GPU, so it's just how NVIDIA does. So now I think the other thing that I'm now interested in is actually how the 12-volt power distribution is done on this card. Because this card, when running various benchmarks on it, pulls about 60 watts from the PCIe slot and pulls about 60 watts from the 8-pin power connector, or around 50-60 watts. Like, it doesn't pull very much from the 6-pin power connector. It pulls less from the 6-pin than it does from the PCIe slot, which I find very surprising because if I was designing the card, I'd put most of the... like, I'd probably not put that much load on the 6-pin, like the PCIe slot. I'd put it all on the power connector over here, because these things are massively under-specced. The difference between a 6-pin power connector and an 8-pin power connector, electrically speaking, is one ground connection. This thing has 3 12-volt connections and 2 ground connections. This has 3 12-volt connections and 3 ground connections. Now, you might be wondering, wait, but this has 8 pins total, and this has 6 pins total. What's going on with the, you know, 6th pin in this and the other 2 pins in this? Well, those pins are being used to detect if a power connector is plugged in or not. And so, yeah, that's why a 6-pin only actually has 2 useful ground connections, and a 8-pin only has 3. But the thing is, you know, this is commonly, like, this is a 150-watt connector, and that's a 75-watt connector. It's like, this is not really, like, physically speaking, this is not half as much as this. This should, if you went with the 150-watt rating, this should be like a 100-watt connector. If you actually go with the electrical specification for the power connector itself, one of these can easily handle 300 watts. I know that because I've done it, and I've never melted one of them. So, yeah, like, I think the thing is, at the same time, like, manufacturers have to get their GPU designs approved by NVIDIA, and NVIDIA is actually pretty strict about sticking to the specification of the power connectors, which is really dumb in my opinion. Well, I mean, it's not dumb for stock operation, but, like, I still think you should probably prioritize this over the PCIe slot. That just seems far more reasonable to me. So anyway, let's figure out how much of the Vcore VRM is connected to what power source. So let's do that. So we're just going to be going off of the capacitor legs, and so we're going to go... okay, so we can see that we have the blue stripe over here on these capacitors. That blue stripe indicates the ground leg. So we're going to be checking just the voltage leg, because these are our input filtering capacitors, right? They're on the 12-volt side of the VRM. We've basically got one for each phase. Yeah, so we're just going to be checking how where these capacitors are connected to. So this first one, I'm going to guess, is probably going straight to the PCIe slot, because of course it is. So that's one Vcore. So we've got one phase of Vcore on the PCIe slot, another phase of Vcore on the PCIe slot, and another phase of Vcore on the PCIe slot. Please tell me this isn't on... okay. Good. Okay, so we've got 3 out of 7 phases of Vcore pulling power from the PCIe slot. I am not a fan of that. Like, I can understand having one phase of Vcore connected to the PCIe slot so that you can boot the card without any power connectors plugged in, and then, you know, NVIDIA GPUs will give you that error message where it's like, you didn't plug in your power connectors. Yeah, you need to be able to initialize the GPU core for that, and so having one phase of Vcore connected to the PCIe slot for having that functionality, very sensible. Having 3 Vcore phases connected to the PCIe slot is like, why? Like, this is literally the weakest power source on this entire board. Why would you connect almost 50% of your biggest power rail to the weakest power source this card has available? NVIDIA. Actually, no, this is pretty... I'd say this is very much on MSI. Anyway, if I had to guess, the other 4 phases are probably connected straight to the 8-pin, so let's check if that's the case. And, yep, that one's on the 8-pin. That one's also on the 8-pin. And also on the 8-pin. And also on the 8-pin. Okay. So, at this point, I suspect that our entire memory VRM is hanging off of our 6-pin power connector. I think. Unless there's something weird going on with our... Yeah, no, those aren't connected, so... Yep, nope, definitely not connected to Vcore. Man, you have a 6-pin power connector, and... Okay, so I'm guessing the entire memory VRM is just connected to the 6-pin power connector. Which, again, we have our blue stripe to this side, so... This leg is going to be... Yep. And yep. Okay, so our memory system is hooked up to the 6-pin power connector. Now, it's worth noting that the memory controller on NVIDIA cards actually pulls quite a lot of power from the memory rail. So I guess the convenient thing about this is that the memory power consumption is actually, like, the power consumption measured on the 6-pin power connector is exactly the total power consumption of the memory VRM. Though I guess we might have some other rails connected to the 6-pin power connector. Let's see. Like, say the Pex rail might be hanging off of the 6-pin. It isn't, then it might be hanging off of the PCIe slot. Also isn't, are you really? Oh, okay, so Pex is off of the 8-pin power connector, and that one's awkward to probe, isn't it? Let's see. Okay, no, that's probably off of the PCIe slot. Apparently not, that's apparently off the 6-pin. Wait, what? Or maybe I'm just probing from the wrong side? I'm not sure where the input capacitor for that little voltage regulator is. Oh, I'm probing from the wrong end of it. Yeah. Oh, wait a minute. I screwed that up. That's the ground side. I'm so dumb. Okay, so this measurement was wrong. I should have just used a screw hole. That's what I get for trying to be fancy. Yeah, so that's supposed to be about 2 kilo ohms, and this is the 12-volt side of that. So now... There we go. Yeah, so 1.8 volts connected to the 8-pin power connector. So I'm rather surprised that, like, the 50 watts is actually just the memory chips. That's like a lot of power. That of course includes the power losses of the VRM itself, but this shouldn't be losing that much power on the VRM, and it is outputting 1.35 volts, so yeah, I guess, you know, that's a decent amount of GDDR6 memory, I guess. It is, what, 8 chips, so kind of a lot. Okay. So How is this wired, though? Like, now I'm super confused. Like, what on earth is this for? Considering that this right here is, like, what's it even connected to? There's nothing there. I guess I'll check that when I desolder that shunt resistor. Because, yeah, like, that is super, like, do we just pass, like, does this pass through to the Vcore rail? Because that's what I would assume it does. Also, I think, if I don't want to, I think what I want to do when power modding this card is actually, and this was an idea I had very early on, is I might, if it's possible, I'd like to move the power distribution so that the Vcore VRM isn't pulling a bunch of power from the PCIe slot. Because, again, like, the PCIe slot is the weakest power source on this entire card. Like, the 6-pin can do more power than the PCIe slot can. The 8-pin can do more power than the PCIe slot can. Actually, if we mod the 8-pin to have 3 grounds, which very easily done, you just bridge these 2 pins over here, because that middle pin is sense. Now, when you bridge the sense pin to ground, you do lose the ability to detect the presence of that power connector, so that's like, not good. You're not supposed to do that, but that is one way to increase the power handling capacity of a 6-pin power connector above what it can normally do. Though, funnily enough, with a GPU plugged into the PCIe slot, because such a large amount of the pins on a PCIe slot are actually ground, a lot of the current that goes in through the 6-pin power connector will actually leave through the PCIe slot. If you basically, like, if you have a GPU in a motherboard and you monitor the, like, 12-volt current coming in, and then you monitor the ground, like, the current returning on the ground connections of the 6-pin or the 8-pin power connector, a lot of the time the return current is really, really low, and that's because a lot of the current will actually be returning through the motherboard. Yeah, that's just kind of what happens with GPUs. So the fact that this only has 2 ground connections really doesn't matter that much. But, you know, if you wanted to add more ground connections to the card, then that's sort of the best place to do it, because, well, this would then have, you know, 12 pins. I mean, three 12-volt pins and then also 3 ground pins, whereas this already has as many ground pins as it has 12-volt pins, so not much point to just modifying that connector. Yeah, I gotta say, like, I'm surprised that apparently the memory VRM pulls 50 watts of power. That's, like, a lot. Yeah, I'm not a fan of the power distribution. I'm really not a fan of the fact that this like, so much power so much of Vcore is put onto the PCIe slot, and the Vcore rail pulls a lot of juice. Yeah, I'm not sure how I can change that, though. Because we do have some, like, power distribution resistors in, say, well, what looks like power distribution pads in this area, right? You see these 0 ohm resistors. And the idea behind these is that basically when you're manufacturing the card, you can shuffle these resistors around to change which 12-volt power plane, well, which 12-volt power source your VRM is pulling its 12 volts from. But we don't have that anywhere near the Vcore VRM. That's just not there. So if I wanted to redistribute the 12 volts power, basically you'd have to, like, desolder this shunt resistor, which is going to really upset the shunt monitoring chip over here, which I'm not thrilled about. Like, that's going to really, yeah, that's going to upset the shunt monitoring chip. Actually, wait, is this? No, that's for the 5-volt regulator. Actually, where is our input filtering inductor for the PCIe slot? Do they just not have one? No, that would be stupid. That would be really weird. Wait, are you... Well, that's horrifying. This dinky little thing is our input filtering inductor for the Vcore VRM. They've got to have the power balancing, like, totally out of whack for this to work. I'm not, like, I'm looking at this like, you know what? You might burn this if you lift the power limit off. Like, this might end up burning up. Because that is tiny. That is a very, very little inductor. Like, look at the size of the main 8-pin power... Like, this thing... This is the inductor they're using for 4 of the phases of Vcore. And then this is the inductor they use for 3 of them. And it's like, I'd be surprised if that can survive 10 amps continuous. Which, admittedly, is way above what you'd want to pull through the PCIe slot. But still, like... Yeah, I am... not a fan. Like, NVIDIA GPUs and their power distribution is always something to behold. AMD GPUs generally just throw the entire Vcore VRM at their power connectors and then everything else onto the PCIe slot because that makes way more sense. You want the rail because the thing is, as you start increasing core power, like, the core is capable of, massively increasing its power consumption relative to everything else on the GPU. And so you really don't want that hanging off of something like, I don't know, a PCIe slot. But, of course, NVIDIA cards aren't designed with, like, for anything other than stock operation. So, yeah, I'm really surprised that they have 3. Like, if it was 1 phase, I'd totally understand that. Like, I was expecting to see, like, 1 phase Vcore, 1 phase memory hanging off of the PCIe slot or something like that. But no, we've got 3 phases of Vcore hanging off of the PCIe slot, which just, yeah. And redistributing the power, now that I look at it, is going to be super difficult. Because this is wired straight to the, like, basically directly to the memory. And the PCIe slot is wired directly to those 3 phases. I guess one way you could work around this, and this is super janky, but this would work around this, is you could run a wire, or, well, yes, a wire. You could run a wire from this shunt resistor up to one of the power connectors. And that way, and then if you just, like, disconnect the 12-volt pins of the PCIe slot, that would solve the whole, like, where's the card pulling all of its power from issue, because you would effectively, like, what you could basically do is, like, cut off the pins here. And I'm not actually going to do that. I think first I will mod the shunt resistor over here. If the thing, because basically the problem is when you mod the shunt resistors, your power readings go completely, like, they go incorrect. And my plan is to replace the 5 milliohm shunt resistors that this card has with 3 milliohm shunt resistors, which will lead to a 66% increase in power limit, which basically means if this is currently pulling 60 watts on the PCIe slot, then after that modification, it will be able to pull up to 100 and around 100. Yeah, it'll be able to go up to around 100 watts on the PCIe slot, which is a lot. So basically what I'll want to do is mod that shunt resistor, check if it's massively overdrawing the PCIe slot, which it might be. If the software is reading that, hey, if after the shunt modification the card still thinks, like, is still reporting 60 watts of power draw from the PCIe slot, that means it's pulling over, like, it's pulling close to 100 at that point. Right, because the card, the reason shunt resistor mods work is because when you replace a 5 milliohm shunt resistor with a 3 milliohm shunt resistor, the card has no idea that the resistor monitoring the current is smaller. So it still thinks there's a 5 milliohm shunt resistor, and it's still doing the power calculations like there's a 5 milliohm shunt resistor. But if you've got a 3 milliohm shunt resistor, in order to get a 5 millivolt voltage drop across a 5 ohm shunt resistor, you just need 1 amp. To get that same amount of voltage drop across a 3 milliohm shunt resistor, you need 1.66 amps. And so basically, if this ends up reading 60 watts of power on a 3 milliohm shunt resistor, it's got to be pulling 60 watts times 1.66, which is, well, totally out of spec for the PCIe slot. It shouldn't necessarily hurt it, but I'm not really, like, I'd rather be I'd rather be pulling 2 times spec for the 6-pin than, 60% over spec for the PCIe slot. These have a lot more margin built into them than this does. So, yeah, anyway, that's kind of it for this video, because I just wanted to take a look at how this thing actually handles its 12-volt power delivery and sort of think about how I want to tackle the issue of removing the power limits. And yeah, I mean, it hasn't really changed anything. We're going to be replacing... what I might do is, because I realize I don't actually have enough shunt resistors, what I might do is I might actually stack one of the shunt resistors that this card comes with, because this comes with 5 milliohm shunt resistors, so if we put 2 of those on top of each other, we'll get like a 2.5 milliohm shunt resistor. Because the thing is, like, I can replace I have 4 3 milliohm shunts on hand, which basically means I have, actually, 1, 2, 3, 4. Oh no, I have enough shunts. I can literally replace every single one of them with a 3 milliohm shunt resistor. Cool, so I actually don't have to do anything. Anything wacky. Either way, if I ran out of shunt resistors, I was thinking of reusing the 5 milliohm ones to stack them on top of the existing 5 milliohm ones. But yeah, that's it for the video. So hopefully you found this somewhat useful, and yeah, thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch, and both the Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check the links to them in the description out. Yes, that was a great way to phrase that sentence. Anyway, that's it for the video, so thank you for watching, and goodbye.